Hi, and welcome back to my Kubernetes series. In this video, I will walk through deploying parts of the openebs storage provisioner. I say parts because the provisioner can do so much more and is really powerful deployed in a large-scale setting. I would love to use some of these features, but for a home lab, such a setup would be overkill and my hardware is not suited for such an implementation. Why, you might ask? When I initially worked with openebs and its advanced storage provisioning features such as CStore, Java, and MayaStore, and their data replication features to create highly available storage, I quickly realized that these storage types are created for large-scale environments. And my hardware was not set up to handle the overhead these storage types required. My suspicion is that providing block-level storage, which then had to be configured and formatted through openebs in Kubernetes to become highly available distributed similar to RAID, was just too much for my cluster. I was, however, able to attach an iSCSI logic unit number, LUN for short, to each node, set up a file system, and deploy openebs's host path provisioner to create and allocate that storage solution to be used by the replicated database we will be setting up in the next part of this video series. In the future, I might look into how I might be able to use the more sophisticated solutions openebs has to offer. Due to the extent of the configurations we have to go through in this part of the video series, I will split the video in two. In the first video, we will go over the setup of an iSCSI target, or the server if you will, that provides the storage as well as the configuration of the nodes. In the second part of the video, we will be deploying openebs, configure the provisioner, and test the allocation of storage to a test pod. First things first, let's talk about iSCSI. iSCSI is defined by the Storage Network Industry Association, short SNIA, as a transport protocol that provides block storage through TCP-based protocol. Block storage is the technology that controls the data storage and storage devices. It takes any data, like a file or a database entry, divides it into equal sizes, and stores it on the underlying physical storage in a manner optimized for a fast access and retrieval. You can think of block storage as a more direct pipeline to the data. By contrast, file storage has an extra layer consisting of a file system such as ext4, NTFS to process before accessing the data. With this theory out of the way, why would we want to set up block storage on Kubernetes? Initially, I asked myself the same question until Nextcloud failed to install with a database connected to an NFS storage. I never managed to get it working with that storage type. As soon as I use iSCSI for storage, for the database, everything worked immediately. That leads me to believe there is something about the faster access to data, which is why I'm applying and deploying iSCSI storage to the cluster. iSCSI, however, is not a shared storage. Unlike NFS, which we covered in the last video, you cannot share the storage between different nodes. Each node needs its own dedicated iSCSI storage. That is why we will set up 5 separate files, which we will assign as block storage to each node. As I do not have a dedicated iSCSI server that I can provide as block level storage, we will create an image file very similar to an ISO you can find online to install an operating system on a VM, add a file system to it, and connect that image file as storage to our nodes. Enough theory for now. Let's set up the server side of the iSCSI storage. To do that, let's switch over to the terminal. Installing the software is really simple. All you have to do is sudo apt install tgt and let the installation execute. As you can see, I already have the latest version of the software installed. As the installation of the software is complete, let's now create the image files that we will then mount on the nodes as storage. First off, you want to select the location where you want to store these image files. If you think back at our last video, we already created such a location under MNT, volume 6, and then kubedata-prod. If we go here and ls, I already created a folder called openebs, which is where I'm going to create those image files. So let's enter that folder. Let's look into it. It's empty, and now we can create the image files. In a larger enterprise, instead of creating image files, I would recommend to build a whole iSCSI storage backend instead. As much as I would like such a solution, due to cost reasons which would be prohibitive, it would not make any sense for me in my home lab. To create the image file, execute the command sudo dd input file dev0, so it's going to be empty, an empty container. Output file would be under MNT, and the path is not correct. Would be volume 6, kubedata-prod, and k8s worker 1.img, count 0, bs1, and we're looking to create 10 gig worth of storage space in this file. Let's go over the options that we're using in this command briefly. Count repeats the copy operation as many times as indicated, in this case 0 times. BS stands for block size, and our block size is 1, and we seek an output of 10 gigabytes. So the copy operation will execute the copy of the block size into the image until we reach the maximum size that we specified within seek. As dev0, the input file that we're specified here is infinite, we don't need to repeat the copy of the block size of 1. We just let dev0 be copied into the output file until we reach the 10 gigabytes. Before we execute the command, however, there is one thing that is still missing, which is a part of the path openebs, because that's where we want the file. Now that it's complete, let's execute. Alright, the file is created. Let's take a look, and we can see that we have an image file which is called k8s worker 1. Let's take another look at the size, lsla, and we can see it's a file size of 10 gigabytes. All we have to do now is repeat the command for worker 2, 3, and 4, and we also want one for the master. That concludes the creation of the image files, and now we can format these and implement a file system. Once the file is written, we need to set up partitions in these image files, which we're going to do with sudo fdisk. We have the image files in the folder in which we're in, so we can go k8s master.img. Within fdisk, we can now add a label for the disk, followed by a new partition. Default is 1. First sector 2048. Last sector. It's a Linux file system at the size of 10 gigabytes. And all we have to do is write. Now let's take a quick look at that image file. At first we're going to empty the screen and get more details. Let's sudo fdisk -l for list K8S master, and then hit enter. We get the details about the total size, the size in bytes, the sectors, and we can see that we have a 10 gigabyte Linux file system in this image container. As I intend to use the local provisioner from openebs, it is required to add a file system to this image file. We will proceed with that step next. As this image does not contain a file system yet, it is not simply possible to mount it on your existing file system. To get around this challenge, we have to use the following command: sudo losetup -- offset. Then we let the system calculate from the byte size, which is 512, times the start sector, followed by sizelimit, and this is another value that we let calculate by using the byte size times the number of sectors, 209.67424, followed by, we want to show everything, find, and then the path, the absolute path where the image is stored, which is in our case mnt volume 6 kubedata-prod openebs, and it is the K8S master. We get the output def loop 0. With that executed command, we mounted the unfinished image at def loop 0 and can now address the image at that location. We do that by executing the command sudo mkfs.ext4, so make file system and an ext4 file system at the location dev loop 0. Enter. Let's clear our screen and see if the creation of the file system worked. To mount this image in a folder and verify the creation of our file system, at first let's create a new folder. I would like that folder in sudo mkdir/mnt test disk. Alright, lsmnt. I have my test disk there. And now I can mount this image by sudo mount -o for options, loop, offset, and again here we want to calculate the offset consisting of 2048, which is the start sector, times 512 as the byte size, which should make it 104.8576. And the image we want to mount sits, it's here, so we don't need the full path. That's K8S master, and we want to mount it to mnt/test disk. Alright, doesn't work. I still have it mounted under dev loop 0, so I have to clean that up first. Let's do that. In order to clean it up, we have to sudo lo setup-d dev loop 0. That now should clean it up, and if I execute the command again to mount the disk, I should have success. Looks like it. So let's go into lsmnt test disk, and here we can see that we have the lost and found, the default folder from Linux, from an ext4 file system. That means the creation of our file system worked. Now that we successfully verified the existence of a file system on the image or in the image, we can now unmount that disk with sudo umount /mnt test disk. This step concludes the setup of the image file, and we will proceed to configure the iSCSI server or target. Configuring the target means to provide the image file as block level storage to another computer in your network. For me in this series, the Kubernetes nodes are these computers. To configure the server, we have to change directories and go to etc tgt. In here, you find targets.conf and confd. All our configuration files that we're going to create for the targets will be saved in the confd folder going forward. By default, the server should consider any configuration files stored in the folder confd. We can verify this assumption by entering sudo vim targets.conf, and then we find a line include everything that is in the folder confd with the ending conf. That confirms our assumption, and we can now create the files in our confd folder. Let's quit out of this file and enter confd. If we ls here, we see there's nothing in here, so we can start creating our own configuration. Configuration files for an iSCSI target are always noted in between target tags. Let's create the file. We need to be sudo vim k8s, and that is the master configuration.conf. And this file has to start with the word target within those tags, and it has to end with /target. In between those tags, you have to provide a few details. For example, the backing store, and now we get to our image file that was stored under mnt volume 6 kubedata-prod /openebs, and then the file name k8s master.img. Next, we want to provide some limiting factors. You don't want every system on your network to have access to this particular share, or this image rather. So you can limit the access to a certain IP address. For example, initiator address is the command to use for that one. Your IP address. You can also then request login details, which we do by using incoming user. So you can provide a username and a password for the incoming connection. You can also provide an outgoing connection authentication by doing outgoing user, and then you can do that username too and password too. Another way of limiting access to your target is to use the initiator name. Every virtual machine, every computer on your network that has the Open iSCSI software installed has its own uniquely assigned name. This name can be used to limit access to a target. This name usually comes in the form of IQN, which stands for iSCSI qualified name, followed by the year, 1993 and the month. Then a naming authority. You can find things like org.debian or com.microsoft. As you can see, it's the domain name turned around, and then followed by a unique name, let's say 1:f. That is another way to limit the access to an iSCSI target. As I do not have the iSCSI initiator's unique identifier available yet, I will refrain from using it here. I will outcomment it, leave it in the file, but I will rather focus on the initiator address, set up an incoming and an outgoing password, and configure the CHAP, which stands for Challenge Handshake Authentication Protocol, to secure my iSCSI target. There is one last item we need to add to the target. We need to provide a unique identifier for this target here as well. Comparing that to the initiator name, it's very similar. So we add IQN for the name, followed by the year, and we're going to take 2023, and we're in September. We're going to then add the domain name, my.kubernetes, and then a unique identifier of the target, and we're going to call this logic unit number 1. With that, the configuration of the target is complete. We're going to write and quit and exit the file. The next step we have to take is to restart our target with sudo systemctl restart tgt, and then we can verify if the target is available. The command for checking that is sudo tgt-adm. It's not tgt, but tgt-adm -mode target --op show. And as you can see, our unique identifier is showing first. We have an iSCSI, the state is ready. It is backed further down by our image file. It has a size of 10 GB and a block size of 512 GB, and there is account information in here, outgoing, and who is allowed to actually initiate the connection. Now that we have successfully set up the target, we can head over to the nodes, install the software, mount the iSCSI target, and see if everything works. I switched over to my K8s master, on which I want to install the OpenSCSI package first. I do that by sudo apt install openiscsci and yes, please install. Now that the installation is complete, let's take a quick look if the iSCSI service is already running. We do that by entering sudo systemctl status iSCSI, open iSCSI. Perfect. The system is running. It's inactive, but it's running. I emptied the screen, and we can now head over to the Open iSCSI folder that was created in order to configure the initiator. We do that by going to cd etc and iSCSI. In here we find the iSCSI ID, iSCSI dconf, which is the file we want to configure. Let's open this file with sudo vim iSCSI d.conf. Change the text so we can read it. And then we're going to go down in the file. Node.startup, we want to change this item, and we're going to node startup automatic. Okay. Next line we want to take a look at is we're going to search, CHAP, here we are. That's what we're looking for. CHAP. As you remember, just a few minutes ago, we set up a username and password on the target side, and that's what we need to configure right here as well. So we want to set the node session auth method. We want to definitely set username and password, and we also need the incoming. So let's start. That was in, and that was in. As you can see, username and password, which aligns to what we had on the target side, as well as the incoming connection, which is the server connection that you have coming back, which is username 2 and password 2. There is one more change that we want to make to this file, which is the authentication method. We want to uncomment the line node session auth method CHAP, and that should be all the changes here. For now, these are all the changes we have to make in this file, so we can write and quit and restart the iSCSI service. We do that with the command sudo systemctl restart open iSCSI. And now we can take a look if we can find the iSCSI target. There is a command which we have to execute, sudo iSCSI admin -m discovery -t st, and then the IP address of our target. Whoops. And as you can see, we successfully found a target that we can now attach to this machine. Emptying my screen again, I want to take another look at the initiator name that is being used right here. Let's at first change the color scheme so we know what is actually set in this file. Do not edit or remove this file. If you remove this file, iSCSI daemon will not start. If you change the initiator name, existing access control lists may reject this initiator. As we have not set up any of those access controls yet, it would be easy to change the name. However, we're going to follow the advice and we're going to just leave this name as is and exit back out. At least we now know what the initiator name is, and we could use it to limit access to our target on the server side. As we already took care of that part of the configuration with the IP address, we're going to leave that as it is. If the IP address ever changes or would ever change, then we would lose access to this particular target. But we will keep all the configuration as they are, and now we will attach the iSCSI target to our machine as a drive. To add the iSCSI target to our machine as a drive, we have to first of all have its name again. So we're going to take another look at sudo iSCSI admin -m discovery -tst -p and the IP address of our server. We're going to copy the full IQN. And then we're going to add this target with sudo iSCSI admin -t -p, and again IP address -l for login, and we have successfully logged in into our target. To verify that, we can enter the command lsblk, and we now see that we have an SDB at the size of 10 gigabytes available. If we follow the same process we applied earlier, we can mount this path to a folder that we're going to create. So we're going to say sudo mkdir-p mnt iSCSI. Okay, now we should have an iSCSI folder. Let's verify. All we have to do now is to execute the command sudo mount, and we again have to work with the option loop and offset, and we have the same offset as before. Dev SDB, which is our block device here, to the folder mnt iSCSI. And now if we add ls mnt iSCSI, we see the default folder for an ext4 file system lost and found, and we successfully created an iSCSI target. We made it available to our initiator, which is the current machine we're on, and we connected this target to this initiator, logged in successfully through the CHAP protocol, and we now mounted this target to our file system. The next and last step that we have to do, we have to make the mount point persistent over reboots, which we do by modifying the fstab file, sudo vim fstab. We can add a line in here. We will start this line with dev SDB, the location where our target is currently available on our system. We will then add the desired mount path, which is iSCSI. Then we will provide the file system ext4, which we have on our image, and now comes the most important option, netdev. If you do not add this option here, you will not be able to restart your virtual machine. The netdev makes sure that the mount waits until your network is up, and only once your network is up and running, the connection to the iSCSI target will be established. You will be able to log in and then mount your target on your current machine. Then we will continue with the loop option, and the last one is the offset, which we also need 1,048,576,0,0. Once we're done with that, we're able to write and quit, and we should be done with our configuration. If we reboot our machine now, the VM will automatically log back in into the target. We'll make it available under SDB. Our modified fstab file will make sure that the target and the block device is mounted to the folder mnt iSCSI, and we can then use it for storing our Kubernetes data on this drive. This step concludes the creation of the image files. the setup of one target, including authentication through the challenge Handshake Authorization Protocol, the setup of one of the clients, including authentication with the target, and the automatic mount of the iSCSI target upon reboot. Please remember, you have to repeat this process 4 more times for each of the worker nodes. Once that is complete, in part 2 of this video, we will add the openebs repository to Helm, download the values file, update our configuration, and deploy that dynamic storage provisioner. Until then, thank you very much for watching. See you in the next video.